In section 4.1, we're going to talk about general vector spaces and subspaces. So we're going to take the idea of Rn, lists of numbers like we've been looking at, and matrices, and expand our concept of vector spaces to include more kinds of things. Before you watch this video, please make sure that you read over the definition of a vector space that I've put on Blackboard. And you should also open up your textbook to this section and maybe read over the first few pages. In this video, I'm going to work through an example, and what we're going to do here is demonstrate a certain vector space. And my vector space is going to be V, the set of functions from R, the real numbers, to the real numbers. And in order to claim that this is a vector space, I have to prove all 10 properties from the definition of a vector space. But before we can get to proving properties, we have to be clear about what we mean by adding functions and multiplying functions by scalars. Here's my definition for adding functions. If I have two functions, f and g, from the real numbers to the real numbers, then f plus g is this new function given by this formula. When I plug in a number x into the new function f plus g, what I do is I plug into each function separately, f of x and g of x, and then add those two together. So the addition here, the actual addition that's taking place, is actually just adding real numbers, because once we plug something into our function, this is now a real number. So this has a name, and you might have seen this kind of concept before in your calculus class or somewhere else. This is what's called pointwise addition. The reason is that in order to add two functions, we add points. We actually have to plug things into the function in order to add the two. And here's my definition for scalar multiplication. It's quite similar to the addition definition. Here I have a scalar c times the function f, and this is going to be the new function given by this formula. So if I plug in x into my new function cf, then what happens is I plug x into f, into my old function, and then multiply that value by c. So multiplying the function by a scalar, in practice, what you do is actually multiply real numbers. So with these two definitions, we've actually proven the first two properties of the definition of a vector space. Essentially, we just have to make sure that u plus v, or in this case f plus g, is an element of our vector space, and also if we multiply by a scalar, c times f, we get another element of our vector space. So now we've proven both of those. And I'm going to prove a few more properties. We're not going to go through the whole list of 10, since that would take quite a lot of time. Next, I'm going to move on to property 3, so just going down the list. And for property 3, we have to show that addition is commutative. So f plus g is the same as g plus f. So in order to show this, I have to show that these two things are the same functions. So that means they need to have the same value when I plug in a number. So f plus g of x is equal to g plus f of x for any x that I might want to plug in. And then you just have to work through using our definitions and properties. So f plus g of x, we plug into each of our two separate functions and then add together. But this addition here is actually just addition of real numbers. And we know that adding real numbers is commutative. so we can rearrange the order, and this is g of x plus f of x. And now we go back to our definition for addition. G of x plus f of x is actually x plugged into the function g plus f. So now we have the equality that we wanted to prove. So that completes property 3. And I'm going to skip ahead to property 5. And property 5 has to do with the 0 vector. Property 5 says that for any vector space, there needs to be a vector, a 0 vector, so that when you add it to any other vector, you get back the vector that you started with. In order to show that, I need to define a 0 function. And my function is going to be this guy. I have 0 with a line over it as my function from R to R. And what this function is going to do for any x that I plug in, it's just going to give me 0. So next I need to see what happens when I add my function, my 0 function, to another function f. And in order to check to see what happens, we have to plug something in. So I have an x here, and using the definition of addition, that means I have to plug it into both functions separately. So I have f of x plus my 0 function of x. F of x will just leave alone, but the 0 function we know just spits out 0. And then this is adding real numbers. The real number f of x plus the number 0 is just f of x. So when I add this new 0 function to any other function, it doesn't do anything. We just get what we started with. And that completes property 5. And to finish off the example, I'm going to do property 6, and I'm just going to leave the rest of the properties. So that would be property 4, and then 7, 8, 9, and 10. Leave those as exercises for you to try on your own. In property 6, what we're looking for is the negative of any vector, or any function in this case, in our vector space. So that means if I'm given a function, I have to find the negative of that function. And in order to do that, I'm going to define this new function. Given f, I define minus f from the real numbers to the real numbers. And this is how it's going to work. If I plug something into this negative f function, then it's just going to spit out minus f of x. So what I want to do is check to see when I add f and minus f, I need to make sure I get 0. So that's what I do down here. Here I have f plus negative f, and I've plugged in some number. And the way addition works is I plug that number into both functions. F of x will just leave alone, and minus f of x, I'll use my definition. Minus f of x becomes, well, minus f of x, but now it's a number instead of a function with something plugged in. So this is the functional way of thinking, and this is the actual number. So this is really just f of x minus the number f of x, and that gives us 0 like we wanted. So if I plug in anything into this function, it's going to spit out 0. That's the 0 function.